Hello everyone, thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Middling Plate, and it is going to provide you the fundamentals of plate bending and also the middling plate theory. I am going to give you an overview of what I am covering in today's video. First at all, it is a bit of background to the topic, and then focus on the middling plate theory and the shell elements before wrapping up with conclusions. Have you ever tried to imagine the shape that a plate will take under load? It is important for understanding how plates work. It is also important for identifying regions with high curvature and moment, and points of maximum deflection. Let's investigate the square plate with simple supports, as indicated by these dashed lines. The white grid makes it easy to see the shape that the plate will take as it is loaded. The curvature is positive, sagging everywhere, and in both directions. You can also see that the maximum deflection occurs at the center of the plate. If we now clamp one of the edges, denoted by the solid line, we discover a negative moment hogging along the clamped edge. The same thing would happen if one end of a beam were changed from a simple support to a clamped support. A plate is commonly identified as a thin flat structure. In order to qualify as a plate, we require that the thickness of the structure is small compared to its length and width. This assumption simplifies the underlying governing equilibrium equations and also allows for several simplifications on the kinematics of deformation due to the thin nature of the structure at hand. In this video, we consider middling plate. The middling theory or first-order shear deformation theory for plates includes the effect of transverse shear deformations. It may be considered an extension of the Chemoshenko theory for beams in bending. The main difference for saying Kirchhoff-type theories is that in the middling theory, the normal to the undeformed middle plane of the plate remains straight, but not normal to the deformed middle surface. In this case, only linear static analysis is considered. Material is considered to homogeneous, isotropic, and linear elastic. Deformations are small enough to use an infinitesimal deformation theory. In linear middling plate theory, the displacements u/v/w at x, y, z are expressed as function of mid-plane deformations w theta x, theta y, where w is transverse deformation, theta x and theta y are rotations of normal. These normal remains straight after deformation, but need not remain perpendicular to mid-plane. This allows shear deformation in the plate. The strain energy of the middling plate considers both bending and shear contributions. The alpha is a shear correction factor and equal to 5/6. The stress and strain components are defined. The bending strength and transverse shear deformations are obtained. The linear elastic stress-strain relations in bending and transverse shear are shown in right-hand side. Now we know the constitutive model and move to finite element discretization. The generalized displacements are independently interpolated using the shape functions of a bilinear four-noded element. Strains are defined. We then obtain the plate strain energy, the stiffness matrix of the middling plate, where dTj is the determinant of the Jacobian matrix. The vector of nodal forces equivalent to distributed forces P is defined. The strain displacement matrices for bending and shear contributions are obtained by derivation of the shape functions. Both the stiffness and the force vector integrals are computed by numerical integration. The stiffness integral is solved by considering for the four-noded element 2 times 2 Gauss points for the bending contribution and 1 point for the shear contribution. This selective integration proved to be one of the simplest remedies for avoiding shear locking. Shear locking can occur in beam, plate, and shell elements. From a mathematical point of view, There is no yield conditioning in corresponding equilibrium equations. The important parameter in the case of shear locking is the thickness of the element. This can be understood most easily with the help of following example. If you consider a plate under combined shear and bending deformations, the portion of the internal energy associated with the bending deformations is proportional to cube of thickness, but the portion related to shear deformations is proportional with thickness. Now if we reduce the thickness, the value of h cube approaches 0 much faster than h, and as a result, all the strain energy of the plate will come from shear deformation. This is not correct because of a thin plate. The bending deformations provide most part of the energy, so the shear deformation beam can lead to wrong results for a very thin plate. This is called shear locking. Now we consider a thinly supported and clamped square plate, side A equal to 1, under uniform transverse pressure P equal to 1, and thickness h. The modulus of elasticity is taken E equal to 10920, and the Poisson's ratio is taken as mu equal to 0.3. In this table, we present non-dimensional transverse displacement results obtained by the finite element method for various thickness values and boundary conditions. In these figures, we show the deformed shape of a thinly supported plate and a clamped plate using a 30 × 30 four-noded mesh. From these results, we know a suitable number of finite elements close to the exact solution. From conclusions, what we learned? The middling theory is useful to model shear problems using finite element method. One Gauss point for shear contribution of shear problems can be the simplest method for avoiding shear locking. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.